Hello, dear ones. You're all welcome to today's lecture. I believe you're all doing well. In our previous lecture, we looked at the power flow of synchronous motors, the torque speed curve, and also we looked at the effect of torque changes on a synchronous motor. Today, we are going to solve one example on what we have done so far. So let's all look at the question together and see how we are going to solve it. The question says that a 208 volts, 45 kVA, 0.8 power factor leading Delta connected 60 Hz synchronous machine has a synchronous reactance of 2.5 ohms and negligible armature resistance. Its friction and windage losses are 1.5 kilowatts and its core losses are 1.0 kilowatts. Initially, the shaft is supplying a 15 horsepower and the motor's power factor is 0.8 leading. So this is the question. And it says that we should sketch the phasor diagram of this motor and find the value of IA and EA. Okay, that's the first part of the question. So let's do it one after the other. Okay, so you can see that the question says that we should sketch the phasor diagram of this motor. Before we can be able to sketch the phasor diagram precisely, we need to find or know the IA and then the EA. Okay, so let's go ahead and find the IA, EA before we come back to draw the phasor diagram. All right, so we know that finding the IA and then the EA, all the values that were given in this question were the line values. So let's use this particular formula to find the line current. Afterwards, then we know how to find the phase current and then go ahead and find the EA. All right. We know that power in or the input power is equal to root 3 multiplied by the terminal voltage multiplied by the line voltage cos theta. Okay. But we were not given the input power. The power that was given to us was what? The output power. It was supplying a 15 horsepower load. So this one represents the output power. But we know the losses. So losses plus output will give us what? The input. So our P input is equal to P output plus the mechanical losses, core losses, and then the electric losses. But once again, the power that was given to us was a mechanical quantity. It said that 15 horsepower, and horsepower is a mechanical quantity, so we need to convert this one to an electrical quantity. So how do you convert horsepower to a watt? Okay, so converting a horsepower to kilowatts, so we multiply the 15 horsepower by 0.76 kilowatt per horsepower. And take note, if you multiply by 0.746, the answer that we will be getting should be in kilowatts. In some books, they multiply it by 746. And if you multiply by 746, the answer that you'll be getting will be in watts, but rather not kilowatts. Take note of that. Don't confuse yourself with the two. So anytime you see 0.746 kilowatt per horsepower, the answer should be in kilowatts. But if you multiply by 746, then the answer should be in watt. Take note of that. So now knowing our output power, we can go ahead and find our input power. Now we have our output power to be 11.19 kilowatts. The mechanical losses, which represent the windage loss, 1.52 was given, and then the core loss 2 was given. So we can input the 2. And then the electric loss, we know that the electric loss is equal to 3 multiplied by IA square multiplied by R. And the question said that the R is negligible, or we should neglect R. So if R is neglected, then it means that the electrical loss rather is 0. So electric loss is equal to 0. So if you compute all this, you're having the input power to be 13.69 kilowatts. Right? So now we know our power. So we can make the IL the subject and then find IL because we know all the other parameters. So making IL the subject, we will have IL to be P in over root 3 multiplied by terminal voltage cos theta. So we insert all the values. So 13.69 kilowatts over root 3 multiplied by 208. We know cos theta was given to us in the question, the power factor, which is 0.8 watt leading. So we input that one too, then we get our line voltage to be 47.5 amps. Okay, so 47.5 amps represent the line current. All right, so the question 2 said that the machine was what? A delta connected motor. So we know the delta connection, the line current and then the phase current relationship. We know that for delta connection, our phase current or our IA is equal to IL over root 3. So the IL that we had, we divide by root 3, then we get our IA. So we divide it by root 3, we get our IA. So 47.5 over root 3 will give you 27.4, but we need to know the angle. The angle too was given to us in the question because we were given a power factor of 0.8 leading. So 0.8, we want the theta angle. So cos inverse of 0.8 will give us 36.87. Then this represents our IA. Okay, so we know our IA. Now let's see how you're going to calculate for our EA. Okay, we know from this formula EA is equal to V phase minus JIX IA minus IA, okay, RA. But since they said that RA should be neglected, so it means that this part of the formula goes to 0. So what will be left will be this part. So now it's just a matter of what? Substituting all our values, then find our EA. So we know that the V phase was given to us in the question to be what? 208 volts. And since this one is a reference voltage, so it will be angle 0. So 208 angle 0 minus our X2 was given to us in the question to be 2.5 ohms. So 2.5 ohms multiplied by the current. The current, you had it to be 27.4 angle 36.87. So if you compute this, you will get our EA to be 255 angle negative 12.4. Okay. The reason why we have this negative is that the EA lacks the V phase. Okay, the EA lacks the V phase. So if it lacks V phase, so it means that the angle delta will be equal to what? Negative value. So the EA, this part 255 represents the magnitude of EA, and then the 12.4 represents the delta, this particular angle, also known as the torque angle. Okay, and this theta, I hope you all know theta. Theta is what? The angle that we get from the power factor. So cos inverse of the power factor will give us theta. So take note of that. So now we have almost all our parameters. So we can go ahead and draw our phasor diagram. So if you are drawing the phasor diagram, first of all, you need to draw your phase voltage first, because that one is always the reference line. So you draw the phase voltage, okay, and we know the phase voltage is what? 208 angle 0.0 degrees. Okay, so we draw the phase voltage, and we said that in the question it was stated that it's a leading power factor. Leading power factor means that the current is leading this phase voltage. So the current comes, and we know the current is 27.4 angle 36.87, where this angle represents the theta. So you write it here. So the current leads the phase voltage, and then we know that the EA lacks the V phase, so we draw the EA2. Okay, so the angle between the V phase and then the EA is our delta, and we know that the delta is 12.4 degrees. Okay, so the other parameter that is left is what? Our G XS IA. Don't forget that we said that RA is negligible or is neglected, so we just forget about that one and focus on this one. So that one too, if you compute our J XS IA, we will get something around 68.5 angle 126.87. That is when you compute only this part. This is what you'll be getting. So you represent that one too here. So this is our phasor diagram, precisely drawn with all our parameters intact. So now we can go ahead to solve the other part of the question. So B part of the question says that, assuming that, let me delete this one so that our this thing will be clear, so that we can go ahead and okay. So B part of the question says that the shaft load is now increased to 30 horsepower. Sketch the behavior of the phasor diagram in response to this change. So initially the load was 15 horsepower. Now the load has increased to 30, which is almost times 2 of the initial load. So they say that we should draw the phasor diagram. But before we can be able to draw this phasor diagram, we need to know the current the EA before we're able to draw, because without that one we will not be able to draw a precise what phasor diagram. So I'll urge all of you to solve C part of the question before you come and do the B part, because the C part says that you should find the IA, IL, EA, and then find the power factor of the load or the machine. So we need to go and find this part of it first. So we can see that if we are to use the previous method to find our IAEA, we will be wrong, because now the previous formula was like P input is equal to root 3 multiplied by terminal voltage multiplied by IL cos theta, where we found the IL, and then after getting the IL we were able to find our IA. If you use this particular method, you will be wrong, because we don't know cos theta, we don't know the new power factor. Don't forget that whenever there's increase in load or change in load of a synchronous motor, the power factor changes. Okay, so we need to calculate for the new power factor before we be able to use this formula. So if you use this formula, you'll be wrong, because we have two unknowns here, the IL and then the cos theta. Okay, but we know that if we are able to use this particular formula, we'll be able to make IA the subject and calculate for IA. Okay, since we know the V phase, we know the XS, and then we can calculate for the EA. Don't forget that the EA is what? We had the EA in the previous example to be 255 angle the delta. And once again, whenever there is increase in load, the delta 2 is going to what? Change. So if you use this particular delta value for our calculation, you will be wrong once again, because if the load increases, the delta is going to open up like this. So there's going to be change in this delta. So we need to calculate for the new delta with respect to what? The new load. Okay, but the magnitude of EA never changes. The 255 never changes. That one remains constant. So we need to calculate for this particular delta. So there's a formula, there's a power formula like this that we can use to calculate for our delta. So our P input is equal to 3 multiplied by V phase E is sine delta over XS. Okay. So let's see if we can make delta the subject from here. But before that, we need to calculate for what? Our input power, because there's increase in load. So the input power too is going to what? Increase. So now our output power, which was given to us as a mechanical quantity, we need to convert to electrical quantity. So 30 multiplied by 0.76 kilowatts per horsepower. We'll convert this one to a mechanical quantity for the output power side. And then we know our P loss to remains constant. That one is 1.5 kilowatts as given in the question. And then our core loss was given to us in the question as 1.0 kilowatts plus 0 kilowatts, which represents the electric loss. I've already explained the reason why this part is 0. So if you compute, we will get our input power to be 24.88 kilowatts. Okay, so now knowing this input power, we know this, we know the magnitude of EA, we know XS. So we're making delta the subject. Delta will be equal to sine inverse of XSP over 3 multiplied by V phase EA. I hope you know how to make this change of subject. If you don't know, see your friend for more clarification, because this one is basic maths. So now we put all our values. XS was given to us as 2.5 ohms multiplied by our P is 24.88 kilowatts over 3 multiplied by our V phase, which was given to us in the question as 208 multiplied by the magnitude of what? Our EA. So we will get a sine inverse of it to give us an angle of what? 23 degrees. So this is our new delta. In the previous case, the delta was what? 12.4. Okay, but here our delta is what? 23, because there have been increase in what? The load. So this angle, this delta needs what? To increase. So it makes sense. If you follow the previous lecture, you understand why there's increase in the angle. So now we know the angle for the EA or our delta. Once again, the delta is what? The EA is leading the V phase, so the angle should be what? Negative. So we'll come and write it in this form. So the internal generated voltage that now becomes what? EA is equal to, take note of this, in the slide we will have something like 355. It's not supposed to be 355, it's a mistake. It's supposed to be 255. 200, make the 3 supposed to be 2, take note of that. So 255 angle negative 23 volts. Okay, so now we know our EA, so we can go ahead and find our IA considering this particular formula. So now we know EA, we know V phase, we know XS. The only unknown in this formula is our IA. So we can make IA the subject and then insert our values and find our IA. So we know that our V phase is 208 angle 0 because that is our reference line. So this is the reference line and it's always at an angle of 0, the V phase. And then we go ahead and put this minus EA. EA is 255. You see, this one is the correct value. 255 angle negative 23 degrees. Okay, all over. Our XS was given to us in the question to be 2.5. So J 2.5 ohms. So if you compute, we are going to get our IA to be 41.2 angle 15 degrees. So this 15 is our theta. This particular theta. This particular theta. The theta for the current. Okay, so we know this, and don't forget that this the phase current. Okay, so we need to find our IL. The question said that we should find the IL, and we know that once again it's a delta connected motor. So for delta connection, we know that our IA is equal to IL over root 3. In other words, our IL is equal to root 3 multiplied by what? IA, if you make IL the subject. So root 3 multiplied by the IA, you will get the magnitude of IL to be 71.4 amps. So this is it. And we know the question said that we should find the new power factor. So now we know theta, we can find the new power factor. We know that power factor is equal to cos theta. So cos 15 will give us 0.966 power factor leading. Okay, take note of that. So now we can see that when there was increase in load, the power factor has increased. The power factor has improved from 0.8 leading to now 0.966 leading. And another thing that has also increased is the delta. Initially, delta was what? Initially, delta was 36 points. When it was operating at a load of 15, the delta was 12.4. Now, when the load increased, the delta also increased to 23 degrees. Okay, let's see the theta. What happened to the theta? Here, the theta was 36.87. Okay, when it was operating at a load of 15 horsepower. Now, when it increased to 30 horsepower, the angle also decreased to 15 degrees. So take note of all those. I made this conclusion in our previous slide, so you can see that this conforms with what we discussed in the previous slide. So now we have everything, so we can go to the B part of the question and now draw our phasor diagram, because we know our EA, we know our IA, we know the theta, we know the delta. So we can go back and solve it. So the B part of the question is that as the power factor on the shaft increased to 30 horsepower, the shaft slows momentarily, and the internally generated voltage EA swing out to a large angle whilst maintaining a constant magnitude. So you can see that the magnitude is still 255, but the angles has now increased from 12.4 to 23 degrees. So now the resulting phasor diagram becomes, so this was the first phasor diagram when it was operating at a load of 15 horsepower. So this was the phasor diagram for that particular scenario. Okay, forgive me for this particular, using this pen is very difficult to get a precise drawing. So now when the load increase now, and this was the current for that particular initial scenario. So now when the load increase, now the current has also increased, but theta, the angle between the current and then the V phase, has decreased. Initially theta was 36.87. Now the theta has now decreased to what, 15 degrees. So take note of that. Whilst the current has what, increased. Okay, the current has also increased. And one particular thing that we will take note of is that delta has increased. Delta was what, 12.4. Now delta has increased to what, 23 degrees, because there's been increase in load. So the torque angle should what, also increase. We made mention of all these things in our previous video. So that is it for today. If you don't understand anything, I'll urge you to take your time and go through the solution once again. If you still don't understand anything, you can post all your comments, then we address them at the appropriate time. Until we meet again, I say stay safe. This is Akinlebe Smart. Goodbye.